In this video, we're going to talk about work, specifically the work done by a force field, and we're going to see how we use line integrals to calculate work. First thing we're going to do here is set up some formulas for how to calculate work. So the context here is, imagine we've got a vector field, specifically a force field, which is acting in space. So our force field, we'll call it vector capital F. And if we don't want to be too specific about the components right now, we'll just say PQR, but these are functions of X, Y, and Z that we've got in the components. So that's describing the force that's acting at every point in space. And let's say that specifically there's a curve C through space that we're interested in. So we're interested in the work that's going to be done by our force field along that curve. Well, in order to talk about that, let's draw a picture of our curve. So let's say this is C. And at every point along C, you could talk about your tangent vector. So your tangent vector, tangent to your curve. And specifically, we want a tangent vector that's 1 unit long. We want it to be a unit vector. So let's say here is our unit tangent vector at a different point. Let's say here, unit tangent vector might look like that. There are 3 formulas for the work done by our force field along our curve C. They're all equivalent, but you may see different versions of this formula in different courses, so that's why we're going to write down the 3 different variations, and then we'll talk about physically where do these formulas come from. So first formula, you can say work is the line integral along C of your force field, dotted with your unit tangent vector, so that's a dot product there, times ds. Another way to say this is work is the line integral along C of f dot dr. So this dr here, that's a vector. We'll talk about that in a moment when we look at the geometry behind these formulas. And then last formula here, work is the line integral along C of p dx plus q dy plus r dz. And when you see this PQR here, let's go back to our context for a second. PQR were the components of that force field. So this last formula here is the most user-friendly formula. It's the one that we actually use for computation. So all 3 formulas represent exactly the same thing, work done by our force field along our curve C. Sometimes you'll see this variation of the formula in a course. Sometimes you'll see this variation. This is the one that we actually use for computation, but they're all expressing the same underlying idea. So let's do a quick explanation of the geometry behind the formulas. And I think it might be helpful here just to label these formulas 1, 2, and 3 so that when we're doing our explanation, we can just refer back to them quickly. So let's look at the first formula. The integrand looks like f dot t. So let's understand physically what vector f dot vector t represents. So this is the magnitude of our vector f, which is representing our force field, in the direction of the unit tangent vector. So let's draw a picture. So imagine that you've got your curve C. Let's say we're interested in this point here. So we draw our unit tangent vector at that point. So it's 1 unit long and it's roughly representing the direction in which the curve is curving. And then remember that you got your force field acting at every point in space. So the vector associated with your vector field here could be pointing in any direction. Who knows what direction it's pointing in? Let's say F is going like this. So in order to understand the work that's being done along the curve C, what we really need to do is resolve this vector F into components. We want one component that's going parallel to our tangent vector, and then we want another component that's going perpendicular. Okay, so if we look at this little red section here, this red vector that we've got at the bottom, which is the component of F in the direction of T, that red vector there is f dot t. Just going back to linear algebra, that's the length of f times the length of t times cos theta. Well, length of t is just 1 because it's a unit vector. So sure enough, that's length of f times cos of theta, where theta is the angle between our two vectors f and t. So that's the horizontal component, or I shouldn't say horizontal, I should say the component of f in the direction of t. Now, if we look back at our integral, we are really taking this f dot t and we're multiplying it by ds, where ds is just a little tiny chunk of the curve. So ds is a length, it's a little piece of arc length here, so just representing how long that little section of curve is. And if you take this vector f dot t that we had over here, and you multiply it by ds, then what you're getting is just a scaled version of this picture. So you're just getting this tiny little vector here. And along this little section of the curve is essentially a straight line. So if we think about units of this, that's units of force times units of distance. So essentially that's giving us the work done by our vector field F over that little tiny chunk of the curve. So if we sum quantities like this over infinitely many of these infinitely short chunks of curve, then what we get is the total work done. So let's say work is that sum, and if you just express that in the language of integrals, you would say, well then work is the integral of f dot t ds, and what are we integrating over? We're integrating over this curve C. So that's where that first formula comes from physically. So now let's scroll back and look at the second formula. So second formula involves this quantity here, this vector quantity dr. So let's make sense of that. Essentially, we need to understand why this vector dr is the same thing as vector t times ds, because other than that, the two formulas look identical. So let's just go through the geometry of those two quantities and what they represent. So we'll just refresh our memories on t and ds here. So t is a unit tangent vector to our curve. So roughly it's giving us the direction in which the curve C is curving, and it's 1 unit long. ds, tiny chunk of arc length, like that. And so if you multiply the two together, then you're just getting a scaled version of your tangent vector. So something like this would be our TDS. So what you could say this represents, you'd say it's a tiny change in position along C. Because our vector t is giving us the direction in which C is curving. If we travel along t, then we're traveling in the direction of the curve. And if we scale that by ds, then it's just a tiny change in position. Okay, but there's another way of thinking about this. Remember when we were talking about parametric surfaces, we introduced the idea of the position vector, which we called vector r, and that just encodes position on a surface. You could use it for curves as well. So let's say our position vector, vector r, just contains our usual coordinates x, y, z. So to say dr means we're just taking the differential of each of these components. So we're literally just passing the differential operation onto each of those components. We get dx, dy, dz. And then if we think about what this means, we would say, well, that's a tiny change, because that's what our differential gives us. It's a tiny change in our variable. And what's our variable? It's position. So it's a tiny change in position. And what are we traveling along C? All right, so vector dr, tiny change in position along C, but that's exactly what TDS is as well. So T, ds, and dr both represent tiny change in position along C. Therefore, we can say that work is the line integral of, well, we said from our first formula, it was vector f dot vector t ds, but we've now just said, well, this vector dr is just exactly the same thing as tds. So dr is literally just a faster way of writing tds. They both geometrically represent exactly the same thing. So that's where our second formula comes from. Some people like this formula just because they feel it's fast to write down. That's the benefit of it. And then from there, it's a very short jump to get our third formula. So if we just sub in here, what is vector f? And if we sub in here, what is this vector dr, then we'll have our third formula. So f is our vector field. And if you want to just talk about a vector field generically without writing down too much detail, then you just call its components p, q, r. So these p, q, are typically functions of x, y, and z. Okay, and then we're doing a dot product with this vector dr, which we said in our previous discussion is just a way of taking the differential of our position. So vector dr is just dx, dy, dz. All right, so what's going to happen if we expand this dot product? We're going to get p dx plus q dy plus r dz. So I would say moving from the second formula to the third formula here is just pure algebra. And I'm going to put a happy face here because that's the formula that we actually like to compute with. So from a physical point of view, I think the two formulas that are important to understand are the first two. In the first one, we really derived the work done by our vector field, or our force field rather, done by our force field along our curve. So we derived that, and then in the second formula, we just said, well, vector dr is a different way of saying vector t ds. And then that leads us to a calculation formula just with a little bit of algebra. So now that we understand where those work formulas come from, we're going to do an example of calculating work. So let's say we're given a vector field. In this context, it would be a force field if we're going to find the work done by F. And specifically, it looks like yx squared. So that's what tells us what our force looks like at any point in the xy plane. Based on that, we're going to find the work done by our force field along a certain curve. So we've got a description of what curve we're looking at in 2D. So it's a parabola, and we're just looking at a certain section of that parabola. So first step in the problem would be to parameterize C. We've got this curve here where both x and y are changing as we travel along that curve, and we really want to turn this into a single variable problem. So we want to introduce a parameter t that describes the different points x and y that are on our curve. Okay, if you wanted to make a quick sketch of this, just if you were interested, this curve here is a parabola. Quick way to plot it might be to think about what the x-intercepts would be. So x equals 0 is an x-intercept, and also x equals 4 is one of our x-intercepts. And then if you wanted to get a better sense of the parabola, maybe sub in another value like x equal 2 and just figure out what's going on there. So when x is equal to 2, y would be 4. Okay, so then by symmetry we can say, well, that's going to be the vertex there then. So there's our parabola, very fast sketch. And we're not looking at the whole parabola, we're just looking at this section from x equal 1 to x equal 4. Okay, so that's what we're going to call C, just in case you want a visual. So what we need is a way to describe this set of blue points that we've highlighted on our curve there. And when your function has the form y equal f of x, an easy way to parameterize is to say x equal t and y equals, now just take your function and replace the x with a t. So 4t minus t squared. And that way you're getting pairs of x and y values that satisfy this relationship. They satisfy y equals 4x minus x squared, but they're all described in this new language of t. And then you also want to capture what t values you're working with. So if x is ranging from 1 to 4 and t is equal to x, then that means t is ranging from 1 to 4. So that parameterizes our curve. And we're also going to need to know dx and dy. So I usually get in the habit of just calculating those once I've done the parameterization. So dx is going to be dt, and dy 4 minus 2t times dt. So now that we've dealt with our curve, let's think back to our formulas for work and figure out how we're going to set this up. So when you're actually doing a calculation, you say work is the line integral along your curve of p dx plus q dy plus r dz. So if you're doing this in 3D, then you have this RDZ term. If you're doing a 2D problem, as we have here, then you just don't use that last term there. So our integrand is going to be p dx plus q dy. Okay, now when we say p and q, those are the components of our vector field. So we need to look back up at the problem. Vector field was the first thing we wrote down here. Our vector field is y comma x squared. So p is equal to y and q is equal to x squared. Okay, I would sub that in right away. So y dx plus x squared dy is what we want to integrate. Okay, and then from there, it just becomes a matter of looking up at our parameterization. We've got all our information here about x, y, their differentials, and also the limits of integration that we're going to be using. So we should be able to just plug everything in here. So y is going to be 4t minus t squared. That gets multiplied by dt, or dx, which is dt. Okay, and then we're going plus x squared. Well, x squared in the language of t is t squared. And then that gets multiplied by dy, which is 4 minus 2t dt. Okay, so I'll put square brackets around that integrand. And our t value is going from 1 to 4. So we've now turned that integration, which was originally in variables x and y, just turned that into a single variable integration using our parameter. So that's why we needed to parameterize the curve. All right, let's clean this up. So we are going to have a big dt at the back. I might as well just factor that out now. And let's write down what our terms look like. So to have 4t minus t squared. And then we need to do this multiplication here. We'd have a plus 4t squared and then a minus 2t cubed. So we can do a little bit of collecting like terms there to get a 3t squared. And I might just write a cleaner version of that on the next line before we do our integration. So we're integrating from 1 to 4, differential is dt, and what we're integrating, 4t minus plus 3t squared. Okay, that's why we're cleaning everything up. Plus 3t squared and then minus 2t cubed. Looks great. So let's go ahead with our integration. We get 2t squared plus t cubed minus t to the 4th over 2, and we're going to evaluate it at 4 and then at 1. So subbing in t equal 4 gives us negative 32, and then we need to subtract off the value at 1, which is going to be 5 halves. So overall, if we put that over 2, that's negative 69 over 2. Okay, and the physical interpretation here, remember what we're doing? We're calculating the work done by this force field along just this blue section of the parabola here, just this finite portion of the parabola. So interesting that the work came out negative here. Want to make a couple comments about that. So when you're calculating work, the direction that you travel along the curve matters. So we were traveling along the curve this way, and we know that because we were told in the problem we're traveling from x equal 1 to x equal 4. So the work done as you move from left to right is negative. That tells us, hey, if we had decided to travel along the curve backwards, if we had gone from right to left, we would have got a positive value for the work. It would have been positive 69 over 2. So you just have to be careful about which direction you're traveling along your curve when you're calculating work so that you get the correct sign. Okay, and then second thing I wanted to just make a comment about is let's understand intuitively, maybe using a picture, why the work is actually negative here, because I think that'll give us insight to our vector field. So let's redraw our picture. So really just doing a rough sketch of the parabola that we drew before. We said that parabola had x-intercepts 0 and 4, and at x equal 2, we checked that the y value was 4. And because that's halfway between our x-intercepts, that's going to be our vertex there. So that's our parabola. And we're only interested in the section going from 1 to 4. So just to simplify this picture, I think I'll just focus in on this section that we care about to make this not too cluttered. Okay, so we just care about the portion of the parabola that's doing that. So that's our curve C. Okay, now let's start plotting some of our vectors from our vector field so that we can get a sense of the forces that are acting at these different points. So remember that our vector field, given in the question, was yx squared. So you can get a sense of the forces that are acting just by plugging in any x and y values that you like. So I think an interesting point would be this point here, where x is 4 and y is 0. So if you plug that in to your vector field, let's see what we get. So if x is 4 and y is 0, and we plug into this formula, we get 0, 16. Okay, so at this point, the force is acting vertically, has a very large magnitude. I mean, if I actually drew this to scale, it would be like way up here. I'm just gonna draw that to illustrate that. Okay, now what we wanna do is then resolve this force vector. Let's resolve it into components. And the components that we care about are the direction parallel to our curve, which will be given by our tangent vector. So if you just imagine our tangent vector would be doing something like this, direction that's parallel to our curve, roughly like that. So if you resolve f, I'm gonna label this here, this is f of 4, 0. So if you resolve that force into components along parallel and perpendicular to your curve, okay, you're gonna get this huge vector going kind of like that, and then another one going perpendicular like that. Okay, this vector is going this way. So now we can start to understand physically why the work might be negative, because certainly in this region, near this point, the force is actually acting in a direction that's opposite to the direction of the curve. Now, at some other points, you may get forces that are acting sort of along the curve. We could try maybe doing one other point here just to illustrate. Let's say we did f of, we know 2, 4 is on our curve. So if x is equal to 2 and y is equal to 4, we get 4, 4. Okay, that sounds a little bit more reasonable. So at this point, our force vector is looking maybe something like that. So there's going to be, if you look at the direction that's now parallel to the curve this way, okay, there's going to be a component of f in the direction of our curve, and then another part that's perpendicular. That wouldn't be relevant here. But the component going along our curve is going in the same direction as our curve is. So over this little chunk of the curve, we could say our force is doing some positive work. But the problem is when we get over in this section of the curve, the force is starting to do negative work, and quite a lot of it. So then summing up over our curve, overall, we get negative amount of work being done by that force field. So that's a little bit of geometric insight into how to visualize your force field acting along a curve, and we got some practice calculating work as well. Thanks for watching.